And I also wanted to thank Simon and Walter and Klaas for inviting me and giving me the opportunity to give this talk. The topic of the talk is maybe a bit divergent from other things we see this week. I will also not say anything about operator spaces today, so Jens did a nice preparation, but I'm going to do nothing with it. So this is a project that I'm working on with Haluk Şengün. It was at Sheffield and works on number theory mainly. And the project is about putting structures in the cohomology of groups that number theorists are interested in a k-homological setting, and in such a way that all the structure is preserved. And the result we obtained so far is that it's actually really natural to think about these things in k-homology and kk theory. So I hope to be able to convey that today. So this something about the setup, the structures that this is about. The groups that Haluk is interested in are called Bianchi groups, and these are somehow three-dimensional analogs of Fuchsian groups. So for a lot of the things I'm saying today, you can actually think about the complex upper half plane and some discrete group acting there, and this will help you to visualize things. But the main examples of interest are actually in the three-dimensional setting. But for intuition, it's really good to think about that two-dimensional setting. So these groups arise as follows. You take an imaginary quadratic field, which is just a concrete field of this form, constructed from some square-free positive integer d. And then you look at its ring of integers, which is some ring, and you built this group PSL2 of OK, because everything sits inside the complex number. So OK is some discrete subset of the complex numbers, and you look at it inside PSL2 of C. Now, there might be torsion in this group, and this we don't want, but there always exists a torsion-free finite index subgroup. And these are the groups we're thinking about. Now, PSL2 of C is equal to the isometry group of hyperbolic 3-space. And for shorthand, I will write always during the entire talk G for this group. So we have G and gamma. Gamma is discrete, and G is this bigger Lie group that gamma lives in. So in particular, such a group acts on the hyperbolic 3-space by isometries. And this means, because it's torsion-free, you can take a quotient, you get a nice three-dimensional manifold. And in the two-dimensional setting, you get some Riemann surface. And this manifold will always be non-compact. So there will be ends or cusps, which look like, well, cusps in the surface case. In the three-dimensional case, this is, for me, very hard to visualize, but there is an analogous thing happening. And this makes these manifolds also quite interesting. You get that the homology of this manifold, the integral homology and the group homology coincide. And of course, since everything is low-dimensional and you have Lefschetz type dualities, you actually only look at H1 and H2, and they are even related. So in fact, only the first homology of this group and the first cohomology, they are containing the essential information. And now it's also true that this manifold, so geometric invariance of these manifolds, actually can be directly related to the field and this ring of integers, and so the number theoretic invariance corresponds to geometric invariance. This is what my collaborator is an expert on. Will not be able to say much about that today. Yeah, the same for homology. Wait, let me see what else there is to say. No, that's okay. So we look at these homology groups.
Homology is the isomorphism of rings.
It's just additive, but it might be true, but yeah. Yeah. But I'm not considering this ring structure at all. Not looking at it. It's not relevant for us. What is relevant is another structure that lives on this cohomology, which is the structure of what is called a Hecke module. And this structure arises in the following way. So there you can view this Hecke module structure, which are operators that act on the cohomology. And they arise from an algebraic perspective or from a geometric perspective. So we'll first describe the algebraic way of looking at this. So we look at a group element in the big group, in the isometry group, the Lie group, and we look at what it does to the discrete group. It may not fix it, so if you want to stay inside gamma, you have to take this intersection. And then we define what is called the commensurator, and these are those elements in the big group G for which the group gamma G and gamma G inverse both have finite index in the discrete group. And so this is a condition on these G. Now, it's known that for arithmetic groups, the commensurator is actually rather big. It's dense in the Lie group. Again, this is not so important for us, but this is a fact. And then you can define operations on cohomology using these elements G. So what you get is an operator Tg from the homology of the discrete, cohomology of the discrete group to itself. And this you get by taking a restriction map. Then there is the conjugation map, which maps gamma G to gamma G inverse. So this is just conjugation by G in the big group. And this maps gamma G to gamma G inverse. But it's conjugation by an element that's not in gamma. So it's not defined on the top level, but just on the bottom level. And then there is a transfer type construction, which takes you from the homology of the small group back to the homology of the bigger group. And this works only because of the finite index assumption. And this is how you can do for any finite index subgroup. You can define this co-restriction or transfer map, which you get from taking a coset decomposition of the small group. So there's a finite number of cosets. You choose some representatives for these cosets. And this gives you a map from gamma to D copies of the smaller group delta using that formula. So if you act with an element gamma on the cosets, they get permuted. And because the image of a coset will be again a coset, this determines elements of gamma, which are called elements of delta, which are called Ti of gamma. So you need to make a choice of coset representatives to get this map. In that sense, it's not canonical. And a gamma I denotes the way the cosets are permuted. And then you define this co-restriction map by just averaging over these elements. And you can show that if you choose different coset representatives, this doesn't change in cohomology, the map. So on cohomology, the map is naturally defined, unique. Now this is just an algebraic construction. And this gives you the Hecke operator. You get this explicit formula by also implementing the conjugation map. Geometrically, it's maybe more natural to look at this construction from that perspective, because you have this element in the commensurator. So you have two finite index subgroups. This means you get manifolds Mg and Mg inverse, which are now finite covers of the given manifold M.
H is three-dimensional.
Yeah, it's three-dimensional, but actually a lot of what I'm saying will just work. This works very generally, because the commensurator, you could take any hyperbolic isometry group and do this on hyperbolic space of any dimension.
It's the same thing as G also.
What?
H.
No, no.
Oh.
H
know,
is
because H
H
is
is hyperbolic space, and G is the isometry group of H. Here it is. So you get this picture where H is the universal cover of these manifolds, and there is the map G from H to H. This is an isometry. And H covers Mg and Mg inverse, which in turn cover M. And the bottom covering maps are finite covers. And this means that what you actually get is what is called a Hecke correspondence, because you get a cover of M and two maps out of it. So you have Mg, you have the usual covering map to M, and you have this somehow twisted covering map which goes via Mg inverse. And then you define Tg on the geometrically defined homology groups by taking a wrong way map, which you should think of as averaging over inverse images in a homological picture. And you push forward via the second map. So in the geometric picture, the Hecke operators are defined like this, and there's less choices involved. It's more canonical to think of it this way. And in the study of modular forms, the cohomology of gamma as a Hecke module plays a pivotal role. I'm not an expert on this, but my collaborator is. So there is really more information here. You have this cohomology group, but you have an algebra of operators acting on it. And this is related to the Langlands program, and many, many people are studying this kind of structure to understand things about these groups and the number theory of these fields. And you can call Haluk if you want to know more about that. I'm learning some of these things, but it goes slowly. And that was also because it was harder than we expected to cast this in a k-homology setting where we really use the geometry of the situation. So if you don't know any of this stuff, it's really not necessary to be able to follow the talk. So we have two ways, a priori, to study this Hecke module. You have the algebraically defined group cohomology, and you have this manifold model, which is more geometric defined homology. And then there is a third picture in which modular forms appear as distributions on the conformal boundary. Now this is also, if you think about the upper half plane, then the real line sits at the boundary of the upper half plane. And if you think of SL2 of Z, for example, then the action inside the upper half plane is nice, it's discrete. The action on the boundary is very bad. It has dense orbits, and it's you cannot study it with algebraic topology methods. And in the upper half plane case, this plays a role in the study of continued fractions and such things. The work of Manin and also my advisor, Matilda Macaulay. They thought about these actions in a noncommutative geometric setting, which was years ago how I came to start thinking about such problems. And our project actually started because we wanted to think about this action of the three-dimensional Bianchi group on this conformal boundary, which is, from a noncommutative geometric viewpoint, a natural object to study, because you can take the cross product, which makes sense in noncommutative geometry, as we know, and noncommutative geometry methods could be a way of attacking or understanding k-theoretic and homological invariance of this action. Another reason why you can think of this is that the quotient manifold and also the upper half plane or the half space in the three-dimensional case, they are non-compact. The natural way to compactify them is to add this boundary, but then you lose the good action. So you leave the world of algebraic topology. But if you are willing to think about C-star algebras, then there's no problem. You can just add this boundary, and look at the action on the compact space. And so you can say that K-homology and K-theory of C-star algebras provide this unifying framework for studying these actions from these three perspectives at the same time. So you look at the manifold, you look at the group, and you look at this boundary, and you can study all these models with the same tools. And the picture, as I described, is you get an exact sequence of C-star algebras on which this Lie group G acts. So this is an equivariant exact sequence. So by H bar, which is H3 bar, but actually this works in hyperbolic n space. You add an n-1 sphere, and you get this exact sequence, which is equivariant. And so also the D of H denotes this boundary. And in particular, for any discrete subgroup, you get an exact sequence of cross products. Now, some words are also in order about these cross products, because I have not put full or reduced, and that's because it's not necessary in this case. So especially the boundary cross product has the property that the full and reduced cross products coincide. So we do not have to worry about such analytic issues, which is why I'm not paying any attention to it. Now, in this exact sequence, these algebras appear, and you get the cross product of gamma with the interior, which is, because gamma is torsion-free, it's well known that this is Morita equivalent to the manifold. So especially when you take K-theory or K-homology, you just see the K-theory or K-homology of this manifold. Then, by using a framework developed by Ralph Meyer and Richard Nest, you get that the cross product of the compactified object is KK equivalent to the reduced group C-star algebra of gamma. And this follows again because we assume that gamma is torsion-free, and then there is an equivariant contraction for compact subgroups, because there are no compact subgroups. So you can apply their theorem and get this result. And then we apply the K-homology exact sequence. So we obtain the well-known hexagon that we've seen also yesterday. And here we see that the groups that appear in this hexagon are really the groups that one would like to study from the point of view of all these three models. So we have a geometric K-homology group, we have the boundary group, and the reduced C-star algebra group. Now I'll emphasize again, this works in any dimension. I've used nothing. This is just there. I also haven't told you how this relates to the usual homology yet. But from our perspective, one could just study this thing. Wait, let's go back. So I told you before that the homology and cohomology groups carry this Heck action associated to elements from this commensurator. And we also know that in the world of K-theory and K-homology, we have Kasparov's bivariant theory, which gives the K-homology groups a natural module structure over these KK groups. So if I take something in the K-homology of some algebra, and I take an element in KK of A, comma A, then I can take the Kasparov product and end up again in the K-homology of A. So it's very natural to think about whether one can put these Hecke operators in the KK groups. And this is actually surprisingly easy to do. So what you do is you observe that if you have an element in the commensurator, then using this map Ti gamma that I had on the slides before, you can actually define a left action of the reduced cross product on the cross product by this gamma g to the power d, because you get d elements in the smaller group. I'm not going to give you the formula, but you can do this. You use the permutation on this free module and these group elements. And this gives you a representation of the cross product in the cross product of this smaller group. And then you embed the module associated to the smaller group in the module of the bigger group. And this gives you an element in kk0 of 2 copies of this cross product. We denote this bimodule by T gamma G and its class by the class of T gamma G. And so this gives us a definition for any cross product, actually. I've not assumed anything about the algebra B. You can just do this. It just uses the structure of the group. In the geometric picture, as in cohomology, it's even easier to do. Because you have this Hecke correspondence, and if you, for example, know the work of Kohn and Skandalis, then you know that this automatically, for free, gives you an element in the KK theory of C0 of M with C0 of M. And the way you do it is you look at the C-star algebra associated to the cover, and you just make it into a bimodule using these 2 maps. Also, there are inner products. It's not a problem. It comes for free. And this gives you geometrically defined operators. And these we denote by TG with an M upstairs. And this gives you this K-theory element, this KK theory element. So we have Hecke operators for any kind of cross product by gamma. And also, if the action happens to be good, you can define them on the quotient as well. Now we know that C0 of H, cross product with gamma, is Morita equivalent to C0 of M, and the Morita equivalence really comes from the universal cover. So this is a construction that I think also most of you are familiar with. So you can complete the functions on H in a C-star module way with values in C0 of M, and the cross product then acts as the compact operators. So this is, again, a very naturally defined geometric thing. And this is the Morita equivalence bimodule. And now you get quite remarkably that not only in KK theory, but really on the level of cycles, if I take the algebraic Hecke module and I tensor it with this Morita equivalence, I get a unitary isomorphism of bimodules where the other bimodule is obtained from tensoring from the other side with the geometrically defined Hecke operator. Now, you would expect this to hold on the level of homotopy, so in the KK group, but it actually holds on the level of cycles. You can prove this. So this shows also that this Hecke operator bimodule definition is quite rigid. It really lets you talk. They can literally talk to each other through this Morita equivalence. And then from this it follows that you get the identity also on the level of KK groups. And this means what I just said in words, that the Hecke action is compatible with this Morita equivalence isomorphism. Now, the next question is, what about the boundary map in this 6-term exact sequence? Because boundary maps in k-homology can be a bit of a pain, because they're not defined by some formula, but they are defined through a Kasparov product with the class of an extension, as Francesca also explained yesterday. So an extension of C-star algebras defines an element in KK1 of C, A. This you could take as an abstract definition of KK1, but there is also the Fredholm module definition. Comment? Sure, yeah. You do need this. You need some condition on the extension. I tried to make this an analysis-free talk. No, so as Johnny showed us in his talk, the elements of KK theory are given by Fredholm modules, or also you can think about spectral triples. And so there is a clash between these two pictures. You have this extension picture. You want to go to the Fredholm module picture. This is a non-trivial task, usually. Kasparov gave us an abstract construction, but that's not always manageable. We can, in this setting, do this in a very nice, more or less geometric way. So we can get an explicit Fredholm module and also unbounded Fredholm module, which I will mention later, representing this G equivariant extension. So this construction is done in a way which doesn't really depend on the group gamma. It really only uses the structure of the hyperbolic space and its boundary, which makes it quite beautiful. We'll only indicate how this works because, well, actually the bounded class is not so hard. The unbounded class requires a lot of analysis. But if I take a point in the hyperbolic space, and I can look at the stabilizer of this point inside the isometry group, and this is a compact group. This group also acts on the boundary, and the boundary is a compact space. So there exists, for each such x, there exists a unique invariant probability measure for this stabilizer. So I get, for each point in the interior space, a measure on the boundary. So I have a field of measures. And they interact very well with the group. So these are called the harmonic measures, and the field satisfies this kind of invariance condition. So if I take the measure associated to a translated point gx, I get a translate of the measure, basically, by the same group element. So this is a nice invariance condition, which is quite powerful for this kind of thing. And you also see that you use information in the interior and you push it to the boundary. So these harmonic measures somehow tell you how the boundary looks when you stand at the point x. This is the kind of intuition that one needs for this. If you have this field of measures, you can define an inner product on the continuous functions on the boundary cross the interior. Denote this by T1 of H, because you can also think of this as the unit tangent bundle. So if you have a point and a point on the boundary, you have a unit tangent vector pointing to this point. And in the literature, people think about this direct product in this way sometimes. And the field of measures now gives you an inner product on the compactly supported functions on this product just by integrating. So it's the usual L2 kind of inner product. And there is a representation of the functions on the boundary from the left, and you have a C0 of H valued inner product. And also the group acts on all the algebras and on this module. And this module will be the module that appears in this extension class. And the operator is just the expectation associated to this field of measures. This defines a projection in this C-star module on which the boundary acts from the right. And now it turns out that this equivariant Kasparov module actually represents this boundary extension. So this is really quite neat. Then there is a construction called Kasparov descent, which means that if you have equivariant classes, you can always get classes for the cross products. This is a standard procedure. And the way you do this is just taking basically a cross product of the module. I'm not going to bore you with the details, but this is now easy to do. And that gives you a very concrete representative of the cross product extension, which gives you the boundary maps in that sequence. And then we get to the following remarkable result, which is that, again, one is after proving equivariance of this boundary map on the level of K homology or K theory. But it turns out that this happens at the level of cycles already. So you get an isomorphism of bimodules, really. So on the right module level, this is not so hard because these two modules are free. You can easily see that that the tensor product is some kind of direct sum. But the left module structures are very strangely defined, and you can actually find a unitary isomorphism that intertwines them, and it also intertwines this expectation operator. So you really have equivariance on the level of cycles again with this boundary class. And so particularly it holds in the KK1 group. So this means that summarizing all these results, you get that this exact sequence, which you just get from the structure of the manifold and the boundary and the group, is equivariant for the Hecke module structure. So all the maps commute. This should already tell us that K-theory and K-homology are a very natural place to study all this stuff. Now we want to relate it to the things that number theorists and geometrists actually study. And for this, we need to be low-dimensional again. So everything I've told you about the exact sequence actually holds in any dimension. But in low dimensions, we have a bunch of isomorphisms. So the K-homology of the reduced C-star algebra is isomorphic to the homology of this group. The K-homology of the boundary algebra is isomorphic to two copies of the homology of this group. And the K-homology of M is isomorphic to a relative homology group of some compactification of M. As stated there, these isomorphisms you get out of Kasparov's spectral sequence. And the last one, the geometrically defined one, follows from work by Mattei, who was a student of Valette and wrote a couple of papers on concrete isomorphisms of K-theory and K-homology with group homology. So these isomorphisms are specific for the low-dimensional case and non-explicit in the way you obtain them. Now we set out this project and try to prove that one gets Hecke equivariant isomorphisms. And for this, you need to actually make the isomorphisms explicit. So you cannot deduce anything about these isomorphisms when they are just spat out of a spectral sequence. One word on the compactification that is used. This is what's in the literature called the Borel-Serre compactification, which is very easy to visualize in the surface case. So if you have a Riemann surface with a cusp, then what you do is you just cut the cusp and add a circle. In the three-dimensional case, you have to add tori, and in higher dimensions, this thing is also defined. And the nice thing about it is that it's defined on the level of the universal cover already, so you add some things to the cusps on the boundary. But there is a bad thing, which is usually the case with compactifications of manifolds, and that this, in general, this is a manifold with corners. So the Borel-Serre compactification is not hyperbolic anymore. And this creates problems. But for topological computations, it's very useful. So here we go. If we have a discrete torsion-free and non-co-compact subgroup, so that was also in the previous theorem, very important. So it's nice to have compact quotients, but that would introduce an H3 term in the computations, and that perturbs things a little bit. So we get these isomorphisms in the non-compact case. And we made them explicit in a way that is compatible with the pairings on these groups. So homology pairs with cohomology in the usual way. And the K-theory and K-homology groups pair via the index pairing. And we can write down these mappings and show that the pairings are preserved. And moreover, we do this by constructing explicit spectral triples for each cohomology class. So this is also some hard work, which I won't be able to say a lot about, but I will indicate how this goes a little bit. But this means we take a cocycle or something in the H2, this relative H2, which is generated by classes of surfaces, and we construct elements in the respective K-theory and K-homology groups. Another thing that happens in low dimensions is that this exact hexagon actually falls apart. And it becomes two short exact sequences. And the one we focus on is this one, which takes K0 of C0 of M and K1 of the boundary, K1 of the group. You can say that from a cohomology perspective, the even sequence is the same. But if one is honest, then it's easier to deal with odd K-homology. For us, it was. I have no idea how to deal with the even sequence. But this is good enough. And this explicit isomorphism of K1 of the group C-star algebra is constructed in such a way that when I get the spectral triple for the reduced group C-star algebra, it actually extends to this boundary cross product. Now, this is a non-trivial fact because the boundary cross product is one of these algebras that, by a result of Kohn, admits no finitely summable spectral triples. You can define an easy map in the case of the group C-star algebra in which all the spectral triples that you see are actually 1 plus summable. And then you know that you have no chance of extending these spectral triples to the cross product. So you have to work a little bit more just to get a representation of the functions that is defined on these spectral triples. Then the first map in this sequence, because it breaks apart in a funny place, the first map is this boundary map, which is hard to compute. And as Jens tried to sell us a little bit, is that when you want to compute a Kasparov product, you better do it unboundedly. Because then you know what to look for. So this means that this boundary class that I described for you in terms of these harmonic measures needs to be made unbounded. This was not easy. And what you do is you look at Riesz-type potential operators, which are integral operators, where on top of the measures, which are parametrized by the interior, there is also a family of metrics on the boundary, parametrized by the interior. And these potential operators are analogs of the inverse of the Laplacian. This is how one should think about this. For me, it was quite surprising when I wanted to do this construction. I came to read all kinds of papers by Russian applied mathematicians who worked with inversion formulae for this operator. So this is a compact operator in the C-star module sense. You can prove that. And you want to invert it. And it turns out that because one works with a sphere here, there is an explicit formula for the inverse, which I won't give you, but it looks like a Lipschitz kind of expression. So you take a difference of two functions and you divide by the distance to the power n plus epsilon. And this you need, so because you can invert this operator explicitly, you can prove that it has bounded commutators with the function algebra. And it's a very specific construction. So that you do to lift this projection operator, this expectation, to an unbounded operator representing the extension class. Another thing that is maybe nice to say is that these operators play a natural role in the theory of Brownian motion, which tells you about what happens when you have a moving particle and when it hits the boundary and all such things. So stumbling upon these operators after the fact was maybe not so surprising, but getting there was quite surprising. And using that, one can state this final theorem, which is that these exact sequences are Hecke equivariant sequences, and the maps are defined using explicit spectral triples. And this result should tell you that, so in the first part of the talk, I explained that studying Hecke operators in a k-homological setting is natural. You have these rigid properties, and this result tells you that you actually recover the same theory in, at least in these low-dimensional cases. So that's making a case for using K-theory instead of ordinary homology to study this Hecke module and the number theoretic invariance that apparently lots of people are interested in. A few words to wrap up on the actual construction. If I have an element in H1 of the group, this is given by a cocycle, and a cocycle is just a homomorphism on the group with values in Z. And the way you construct the spectral triple is in that explicit way that I've written. You take L2 of the spinors on the hyperbolic plane, you tensor it with Z, so this is just an infinite direct sum. On L2 of Z, you have this number operator, and on L2 of H comma S, there's a special gamma H operator, which I will tell you in a minute what it is. This data here, I should say that the representation of the cross product is where a lot of the information is. I'm not giving it, but this is defined in a way that also uses information from the cocycle. And this gamma H operator is the gamma element, which Kasparov constructed in this hyperbolic setting. But it's an unbounded version of that, and you need to tweak it a little bit. And I'm also lying to you because this object there, this one, is not really a spectral triple. It doesn't have bounded commutators with the group elements in the algebra. But the commutators are unbounded, but in a controlled way. And this means that the bounded transform still defines a Fredholm module. And that's, you need to tweak this gamma element in such a way that you get controlled unbounded commutators. This is a general problem. This is actually related to Jens's talk. So Jens talked about how twists appear when you take unbounded Kasparov products. This is a kind of connection operator. And when you construct these operators, twists naturally appear, so you get bounded twisted commutators. I haven't checked this in this example, but I think this also happens. But because I want to take a sum, so this is the general problem when you study the unbounded Kasparov product. You have something twisted here and something untwisted here. You want to take their sum and prove Fredholm module properties. You cannot do it. Or at least we have not been able to do it just yet. But in this case, you can control the unboundedness of these commutators here. So I'm not using the twist. I'm doing some kind of logarithmic construction, which gives me the right index theory. And for this project, I'm happy about that. And the other map, which involves the boundary map, is constructed in the following way. So we have an isomorphism of this geometric k-homology group with a relative group, which is not so nice, because it uses this non-geometric compactification. But it turns out, again, follows from low dimensionality and these results of Mate that elements in this group are represented by surfaces which are potentially surfaces with boundary, but their boundary is inside the Boyer-Serre boundary. And because of the specificness of this three-dimensional situation, you can show that the interior of these surfaces are hyperbolic surfaces. So they have a nice Dirac operator because they are complete. So this gives you a self-adjoint Dirac operator. And then you again use the unbounded Kasparov product, but this time with the extension class, to get the other half of the spectral triples on this cross product. So remember that in the Kasparov spectral sequence, the K-homology group here was 2 copies of H1. And here you see that you have 2 very different families of spectral triples, distinguishing the 2 copies. So it's also true that these guys here commute with the functions, almost, and not with the group, whereas here it's the other way around. So there are really 2 kinds of spectral triples on this boundary algebra. And you also see that this construction is much more geometrically inspired using the surfaces and this Brownian motion type operator, whereas this is really a fairly algebraic construction. I think that's what I wanted to say, so thank you for your attention.
Thank you, Bram. Any question, Mark? Yes.
Is it possible to say, just in a few words, what you mean by the operator in the top display? So that they don't have bounded commutators, but they do have them in a controlled way.
Yeah. Well, this means that if you take a group element and you take the commutator with this operator, then the unboundedness of this commutator is actually controlled by the unboundedness of this operator. And that means that if you hit the commutator with the resolvent of the whole thing, it will still be compact. And this is the same phenomenon that Magnus and I saw in our Krumskruger paper. We called them epsilon spectral triples because, yes, they are. So your commutator is unbounded, but just a little bit less than the resolvent of the entire thing, and this is what saves you here.
Yes.
I have 2 questions. What's the connection?
Yeah, that involves the Poisson kernel. So you have this inner product on this L2 of T1, and this is isomorphic to a trivial module by a map that uses the Poisson kernel of this field of measures. This gives you connection, and this also creates some analytic subtleties in the definition of that operator. Indeed. I don't know. What do you mean by this? Yeah, I think so. But I'm not 100% sure, but I think this is the case. I think that's also why they have that name.
Yes, Matthias.
Yeah, what sort of problems in number theory are addressed by this formalism? I know some, the Riemann hypothesis, the Goldberg conjecture. What sort of number theory is this about?
This is about what I'm told. I mean, I will also be very honest with you, and I'm not an expert on these things, but what Haluk, my collaborator, works on is this Langlands conjecture kind of thing, where the construction of automorphic forms, so modular forms in dimension 3, is very hard. And this project, which, I mean, this is a paper which is almost written, but should really be viewed as a starting point. And the construction of these automorphic forms, so in dimension 3 there is a problem when you compare it to dimension 2, because in dimension 2 you can use algebraic geometry techniques, but in dimension 3 that kind of thing is not available. So that's why he was also interested in trying to pursue this kind of direction, to see if there are other methods that that allow you to tackle computations here. But getting the cycles here was a bit more involved than we initially thought. So the project really started to be centered around that and these constructions, which we have now done. And the number theoretic questions would be for the next paper.
But is the logic, if I understand understand that in dimension 2 you have uniformization and Riemann surfaces and theory like that. And
Yeah.
this is understood.
So you have a complex structure,
And
basically.
Dimension 3 you don't have any of that. And
Yeah.
you look for something else.
And yes, so you look for something else, and it's also the issues with the conformal boundary and understanding the conformal boundary and how modular forms relate to these distributional techniques. A lot of papers are written about that. And this was actually, so Manin and Marcoli did work on this in the mid-2000s, which was also in that sense tentative. So studying the conformal boundary with NCG techniques allows you at least to associate homological invariance to it, which from an algebraic topology perspective you cannot do.
Okay. Any other points from everyone? Okay, let's thank our speakers. So we can move to the third